pleasure to continue the series of lectures by Bo'az Klartag. So today he will talk on isoperimetry in convex bodies and Eldan stochastic localization. Please.
Okay, thank you very much, Alina and Yosef. And also thanks for the audience for returning to the second lecture. And indeed, this is in a sense, a continuation of my lecture from Friday. But on Friday, the lecture was more focused on formulation of the results, description, and a bit of motivation and history. And today, the plan is to discuss the proofs and the techniques. And before I start, I want to urge you to stop me at any point and ask questions and make comments in something is not clear. Okay, it's not a big audience, and we can definitely ask questions during the lecture. Don't have to wait until the end. Okay, so we'll work with mu. Mu will be so, okay, this is related to some. This is unrelated to the lecture. Okay, so I should move it. Yes, sorry. Okay, so we'll work with measure mu, which is some probability measure in Rn. And the density will be denoted by P. And like on Friday, we'll assume that P is log concave. Let me remind you or tell you if you never heard about it. Log concave means that for any 2 points, x and y, if you look at the convex combination, then the value of the concentration is larger than the geometric average of these two values for any x, y, and lambda between Rn and lambda between 0 and 1. Okay, and equivalently, it means that if P is of the form E2 minus rho, let's say rho is smooth, then equivalently we assume that it means that rho is convex. So its Hessian is positive definite, semi-definite everywhere in Rn. This is log concavity. And as we said on Friday, the main examples for log concavity distributions are first, the uniform distribution on any convex domain, any polytope is log concave, and second, the Gaussian distribution in Rn, and all of the Gaussians are log concave. Now, we would like to study the isoperimetry constant, so let me define it. So I heard that Yosef calls it the Cheer constant, so let me also use this name. I actually don't know what's more common, both are pretty common. So what is it? So this is the quantity psi mu, which is the infimum over all subsets of Rn, say with smooth boundary, all domains on a smooth boundary. And we look at the ratio of the measure of the boundary of the set A divided by the minimum of the measure of A and y minus the measure of A. Okay, and the boundary, I should explain what it means. It's the integral over the boundary of P, of the density. So for example, if your distribution is uniform in some polytope, maybe this quadrilateral, I don't know, then you look on all subsets A, okay, and you try to minimize the surface area that the boundary of the set A, the measure of the boundary, the size of the boundary, divided by the minimum of the measure of A and 1 minus the measure of A. Okay, what's the relation between isoperimetry and log concavity? So we discussed some things on Friday. We said, for example, that the spectral gap of the nominal Laplacian, the Laplacian associated with mu, or the Poincare constant, if you want, are determined up to factor of, I don't know, 5 or 10 or something like that from the isoperimetric constant. This is something we saw, and we also discussed, let me recall it, this result by Sternberg and Zumbrunn, and that was proved, it was generalized. Okay, this was discussed in the convex body case, but it also works in the log concave case, as was proven by Manuel Milman. So, so in the log concave case, you can say that the infimum, it's enough to look at sets of measure 1.5. Okay, so let's call this star. So for the infimum in star, it suffices to look on sets of measure 1/2. Okay. Now the main question in this business of isoperimetric convex bodies, which is still open, although it is less open today than it was 1 year ago, is the KLS conjecture. KLS is Cannon, Lovász, and Simonovitz. Lovász, I think, just got the Abel Prize. It was from 1995. And they conjecture that under this convexity or log-concavity assumption, the best way to do is to bisect by a hyperplane. That's the solution. So up to a constant, factor 5 or 10 or so, the best is to bisect by a hyperplane. Okay, so that's the conjecture about the isoperimetric polynomial convex set. So if you want it more formally, so the claims that there exists, let me emphasize. So from now on, the letter C will always stand for some universal constant that does not depend on dimension. But for the first time, I'll do so for this constant depending for any n and for any mu log-concave in Rn. If I look at the isoperimetric constant psi of mu, then it is at least C times the same infimum as before, but the infimum only run on half spaces. Okay, so I look at the ratio of these the boundary and the size of the set and its complement, and that's the conjecture. Now, of course, psi of mu is at most what's written here without the constant. And that's because it's an infimum over a smaller set, only half spaces, and not all measurable sets with smooth boundary, like in the definition. So the conjecture that it's not much smaller, so it can only be smaller by universal constant. And by the way, already in dimension 2, you could get a constant if you look on a bad example. So a constant is indeed necessary. Okay, in a half space, I mean, I guess everybody knows, but let me. So half space, you take a hyperplane, you take one side of it. That's the half space. Okay, some remarks on this conjecture. What those that were more or less, yeah, they were mentioned on Friday, but the first one, but I repeat it. So this conjecture implies Bourgain slicing conjecture, and optimal estimates in the center limit theorem for convex sets. The second conjecture, the second remark, is that if I look at this quantity here, let me call it the square here. So the right-hand side here, okay, the infimum of half space is really easy to compute. I mean, well, easier to compute, let's say. So why? Let me define the covariance matrix of the measure mu. Let me try the vector value notation. So I'm integrating x tensor x d mu x minus the Barrett center tensor itself. And this tensor just means this is the matrix of xi times xj. It's matrix valued integral from 1 to n. And d mu is the Barrett center. Okay, so that's the covariance matrix. Just its ij coordinate is the covariance of the xi and xj, the I and j coordinates of the random vector distributed according to mu. Now, the claim is that this infimum, the infimum over half spaces, is equivalent up to universal constant to the operator norm of the covariance matrix to power -1/2. Okay, why is it true? Let me also say. So this was we had this this observation by Hensley from this theorem by Hensley and by Frederici, which tells you that for any direction theta, if I look at the covariance, the variance of mu in this direction, so this is roughly 1 over, so this times the supremum of the largest section orthogonal to theta. So this is a universal constant. This is at most 110 and at least 1 over 10, 1/10. Okay, and this basically, this followed from Minkowski type analysis or Park-Palendler, and the idea was that if you project, take the push forward to direction theta, you get a log-concave density. You get density. So this is the density distribution of in direction theta. So you push forward under x times theta, and kind of this is the variance, the square of the variance, and that's the supremum. And for log-concave distribution, this times this is roughly the total area, which is 1. So it's probably distribution. That's roughly the explanation. Okay, so anyway, so if you know that the covariance is identity, then you say that mu is isotropic. This was our terminology. This is the definition for the word isotropic. And Kelly's condition is equivalent to saying that for any mu log-concave isotropic, psi of mu is at least a constant. Okay. Now, if you want the things that depend on dimension, then you look at psi n, which is the smallest possible psi of mu. Mu log-concave isotropic in Rn. And the best result, so I discussed the history on Friday, so many contributions along the way. The best result is not to date is chain bound from this here, which is that this goes slower, this decays above a power law. So for any epsilon, there exists some C epsilon such that psi n is at least over n to the epsilon. Okay, so if it goes to zero, it goes to zero very, very slowly. So something like log or so. Okay, no, it's not a log. What actually Chen proved this here is that e to the minus root of log n and some log n. Okay, now, so that this is, yes, please. Good. Thanks for the, yes.
Hensley, 110 and 10, does it depend on dimension or it's universal?
No. It's much better. First of all, it's much better than 110 and 110, and definitely does not depend on dimension. That's the whole point. I cannot allow, nothing can depend on, if unless, so for me, it depends on dimension should be mentioned explicitly and with lots of warnings around. All constants are universal constants, do not depend on dimension in particular. I think on Friday I gave better constants than 10 and 110. I think I gave square root of, I remember square root of 6, square root of 12, something of this form, but I can find out if you want the type constant.
Okay, thank you.
Okay. But this is the range between two constants, and this is really the truth. Any further questions? Thanks, dear. Okay, so KLS is when you normalize the covariance, basically, right? You have a local distribution, convex body, and you assume that you chose the right units in many multi-dimensional units. You normalize the covariance, and then you want to find a probability problem. There is another easier approach, which is to make uniform log-concavity assumption. So not just to assume that, okay, the Hessian is non-negative, but to make some explicit lower bound for the Hessian. And this was known for many years. So, so we have the following theorem. So it's okay, I call it more log-concave than the Gaussian. Just to remember, and this theorem is due to Bakri-Nidou from 96. It's analog of results in Riemann geometries that were earlier about the Ricci curvature. Okay, so we assume that our measure is S density E2 minus 4, and there is some parameter T such that the Hessian of rho it has to be non-negative, right? That's low concavity, but no, I want to assume a bit more. At least T everywhere. Uniform estimate for the low concavity everywhere in Rn. Then the conclusion is that, so this in particular implies that the covariance is at most 1 over T. Okay, so this is, if T is 1, it is stronger requirement than being isotropic. It means that it is even more, it's more low concavity than a Gaussian. Okay, it's more centered, more concentrated than a Gaussian. Then half is at least constant over root of T. This constant, Dima, I think it's root of 2 over pi, but I won't dare write it down. This is what I believe, but I'm not sure completely. Anyway, this constant is what you get for the Gaussian. And the Gaussian, relevant Gaussian is Tx squared over 2. Okay, so, and this condition of having Gaussian adjunctive means that you're more low concave in this distribution, right? This is the quality case. How did people prove these theorems? Are by now many proofs. So the first proof in that paper Bakri and Edu was using called gamma 2 calculus, Bakri type calculus, and ideas of Bobkov from the proof of asymptotic for the Gaussian measure. There are two more methods that I want just to quickly mention. One of them is using Caffarelli contraction. So a few years later, I think 1999, Caffarelli discovered that not only the isoperimetry constant is better than what you get for the Gaussian, but actually there is a map pushing forward the Gaussian to the measure mu, which is a contraction. Okay, so it is really more concentrated, more localized in the Gaussian in a very strong sense. You can push forward the full measure using a contraction, and this implies that the isoperimetric constant gets larger. Another proof, which is more relevant to us today because it is related to this recent progress on KLS, which is one of the topics of this lecture series, is convex localization. This is a method. You could say that it was mentioned first by Payne Weinberger in 60, but this was not very rigorous. And actually, I mean, most of the ideas were presented in a paper by Gromov and Milman from 87. And the method was further developed by Lovich and Simonovich and by Kalanovich and Simonovich just 2 years earlier. Okay. And let me tell you the idea. So the idea is to do hyperplane bisections. So let us try to prove, okay, we don't assume any uniform bound on the low concavity, just low concavity distribution. And suppose that we have some subset A in Rn, that has measure 1/2. And my goal is to bound its surface area with respect to mu. That's my mission. And I will not do isotropicity, I just say that this is at least 1 over the diameter of the support. If it's a convex set, 1 over the diameter of the convex set. That's at least what we try to get from this method now. So the idea is that I want to find the hyperplane H. Okay, so say this is a okay, mu is a uniform in a convex set. And the set A is 1/2, so maybe this is A. And I just find the hyperplane, the purple hyperplane, like this. And what's the property of the hyperplane? The hyperplane is 2 sides. One of them is this is H, this is H plus, this is H minus. The orientation does not matter. And now what I require is that not only A is 1/2 of the total mass of U, but also in each part, in each half space, it's exactly half of the total half space. Okay, so it has the same proportion in each of the half spaces. And there is a simple topological argument, very elementary to find such a hyperplane A. It's not so complicated. Now, what did we gain? Now we split our problem into 2 small problems. Now you can work separately on each half, on each part, on each half space. In each of them, if you restrict the measure, you get a log-concavity measure, normalize it back to get probability measure. And now you want to show that in each of these pieces, the boundary is at least 1 over the diameter. The normalized boundary, normalize it to probability measure, so the boundary is really half of the diameter. That's your goal. And the idea now is to bisect again and again Okay, so we reduced one problem to two problems, but now we do it again. We bisect here like this and here like that. So it's after two sets, let's say you have four problems, four pieces in the decomposition, and then 8, etc., etc., etc. And if you run this process, then in the limit, you get a partition into objects of lower dimension, but they will be convex again, and the measure will be log-concave again, thanks to Minkowski. So then you can use induction on a dimension. And by that, you know that at least one of the surface area on each piece is at least one over the diameter in smaller dimension, and that's how you roughly work with hyperplane bisections. So this is very roughly in a nutshell the idea of this method. We'll not use it as is, but that's kind of a motivation for us. And another thing about this induction on the dimension of this bisection, what you get at the end is some kind of a needle decomposition. So you decompose your measure into pieces which are still log concave and kind of look like needles in some, if you have imagination. Okay.
Excuse me,
yes.
which part is lower dimensional on the
so okay, so but you bisect again and again, and you get final partitions of your original convex set, right? At the end step, you get partition into 2 to the n parts. Now let's take the limit of this process. If you take the limit of this process, it's a very non-trivial operation. You need to work very hard, but it is possible to take the limit of this process and to obtain this integration of measure. So the full measure of the convex set is expressed as the mixture of measures on lower dimensional objects. This is very roughly. So you can read about it in these papers. By the way, there's also a paper by Alesker that is kind of an explanation of the Grove-Millman paper, in which this Rochlin partition and this measure theoretic aspects are explained in more detail.
Thank you.
Okay.
So the scaleless conjecture about bisecting by hyperplanes.
Yeah, still open.
Is it? Do you think something similar would hold in the Romanian case? Let's say, hyperbolic
That's a
plane.
very good question. Under positive Ricci, let's say.
Positive Ricci, yeah. So
yeah.
Like totally geodesic.
No, you cannot. No, you don't have totally. No, maybe in some group theory or something. I mean, if you have homogeneous.
Like I don't know, maybe like symmetric spaces or.
Okay, in symmetric spaces. Okay, symmetric spaces are not. Yeah, I mean, okay, symmetric spaces are, I think, much easier than when. No, I mean, there are a few of them that are full of symmetries. Maybe the negative curve. So I would say in symmetric spaces, the interesting case is the negative curve. You are an expert, not me. But I would say that the negative curvature, where this complexity comes from topology and how many holes you have in the toes and things like that. And here the complexity comes. So the positive Ricci case would be. I mean, what do you have? Grassmannian? Or I mean, there are not so many examples.
Anyway, no, this is kind of an idle question.
No, it's a good question. So actually, yeah, so somehow in positive Ricci, you have kind of mixing locally, some kind of local effect of curvature helps you. And in the negative curvature, it's more global things that give us a predict. So I think it's different reason for that supermatic inequality in negative curvature and positive.
Okay, yeah, thanks.
Okay, please go and ask us more questions. Okay, now Eldan stochastic localization. So this was kind of a motivation, but I'm going to explain to you in details this method. It's actually in the title of this lecture, so I should talk about it. And actually I discussed the Liebenpaller version of this. Okay, so what's this thing? So there are, first of all, it is inspired by convex localization. And second, there is no need for uniform log-concavity. Maybe I should write it. So in convex localization, everything should be uniform because you don't control what's going on in your partition. And here, some kind of average conditions are enough, average like isomorphicity. Yeah, in the Riemann case, I would be happy just to formulate a good conjecture in positive Ricci case. I mean, at least for me, I know the techniques of positive Ricci is no more. It won't be totally geodesic, but something. I don't know exactly what could be the conjecture. Okay. Anyway, you can discuss it later. So this is the idea, and the main feature of this Eldan's method from his PhD is that you decompose your measure, you compose it into pieces, but these are not geometrically disjoint pieces like in this localization, convex here, but we have overlap, is composition into measures, okay? And each of these measures is more log-concave than a Gaussian. Then into minus t squared, say, for some parameter t. Okay, so that's the idea. Okay, how would you construct what it is exactly? There are several constructions. The more common one, which is maybe what Johansi will explain tomorrow, I'm not sure, is to take this hyperlink bisecting procedure and change in two ways. First of all, you make it more gentle and continuous. You don't bisect, but you kind of add weight and reduce weight. And second, you do it stochastically, you do it randomly. That's one construction. But there are other constructions, and today I think I'll try to present a construction using Bayesian statistics. Okay, it's not better and not worse than the other construction. One reason why I want to do it is because if someone with background in statistics like Johansi can prove mathematical theorems, then maybe a mathematician like me can talk about Bayesian statistics. Let's see if it will succeed. Good. So what is the construction? So what's the setup? The setup of this Eldan localization is as follows. You have X will be a random vector. It's this, what we had mu earlier. Now it's a random vector with density P. The same, instead of mu, I talk about X, but I want to call P P0. Okay, and replace P by P0. Moreover, I want to have a Brownian motion. So this is a Brownian motion Rn. With start at 0, independent of X. Okay, now this is a seminar in geometric analysis, so I'm not sure if everybody is familiar with Brownian motion. So let me just say a few words about Brownian motion. So Brownian motion, it's kind of, okay, dimension one, at least I can draw it the graph. It's a random function starting at 0 and doing kind of this fractal type things in dimension 1/2. It's order 1/2 roughly. This random continuous function typically fluctuates at distance t, some kind of reaches something like root of t. And in fact, if t is larger than s, wt minus ws is Gaussian, centered Gaussian of variance t minus s. So the standard deviation is square root of t minus s. Therefore, the typical deviations are root of the thing. The increments are also independent. Another point of view is to view this random function as a random element of the space of continuous functions, which are Rn valued. Okay, this is so this is a random element of this space with respect to the Wiener measure. Okay, so in this space there is this the Wiener probability measure. We denote it by PT. Okay, there is one computation that I want to present, which actually can leave as an exercise if you've never seen. Okay, these computations appear, say in a paper by Cameron and Martin for 1944. Okay, so let's fix a vector x in Rn. Okay, and let us look at the process, which is, this is kind of a change of variables theorem for a very simple change of variables theorem for the Gaussian measure, for the Brownian motion. Let me look at Wt, the Brownian motion, plus Tx. Okay, so that's another random function. Okay, if x is a large vector, it behaves differently, right? I mean, you add t times x, so at large time it is closer to x than the Brownian motion. But still, it's a random. It is distributed in, it's a continuous function distributed in this space. Let's call it omega this space in a certain way. So let me tell you what's the density of this function, this random function in that space. So it has density in omega with respect to the Wiener measure, which equals at the point, let's say alpha t. This is the point in the Wiener measure. So what you get is e to the alpha t. It only depends on the endpoint. Alpha t x minus t x squared over 2. Let's stare for a second here. So what does it mean? It means that with respect to the Wiener measure, you put more mass to curves. So if this is, let's say, so this process should be more, if this is tx, it should be something like fluctuating around this thing. So you put more mass to trajectories, to paths, to project, okay, to curves. I won't say passes just because I pronounce it in a way which is an offense to the English language. I'll say curves. So just you take you have these curves that are kind of closer to this linear line t times x, and if you reach a point which is a large scalar product with x, you give it much more weight than if it's a small scalar product with the vector x. Okay, so it kind of makes sense, at least something about it, but it's a formula that you can prove in many ways. So this is the density of this process with respect to the Wiener measure. Okay, now comes the following construction. So remember that we have this random vector x and we have the Brownian motion, and now we consider the process theta of t, which is t times x plus wt. Okay, so what's going on here? I have this drift vector x, and it is random. It has nothing to do with the Brownian motion. So there is this drift which is dictated for the entire process. This is the vector tx, and then wt is doing some kind of fluctuations of all the root of t above this line. Okay, so that's the way we look. That's the way this process behaves. Okay, and again, x and wt are completely independent. X is just a vector in R and tells you the drift, the direction in which your process is going to drift asymptotically, if you want, and wt is independent Brownian motion. And I said the word asymptotically because if you look at the limit of this process, then you're going to get x, because the fluctuations of the Brownian motion are just root of this, so they go to 0. So almost surely you can recover x from logic of this process. And now let's play the following experiment. Suppose that I sample x and sample the Brownian motion, and I send to you theta t. Okay, with time, and your goal is to guess what was x. That's the rule of the game. So let me write it. Okay, so suppose that an observer is given a sample of theta t with time. So up to time t, it only sees, I mean, the values of theta s for s smaller than t. And the question is, how can the observer estimate the unknown drift? Okay, the vector x. That's the game. Okay, is it clear? Someone sent the observer theta t up to time 1, for example, and then the observer needs to guess. Of course, if the observer sees the entire process theta t, the observer can just compute this limit and tell you this is the limit. But at shorter times, it's harder. So how would you compute? What's the strategy of the observer? Here's the Bayesian strategy. So a Bayesian person is a person that has an opinion, a probability distribution for everything in the world. So in particular, what would the observer say? Okay, first of all, let's say what would the observer say times 0? At time 0, the observer just sees that theta 0 equals 0, just the first point of the process. This is no information at all. So what can the observer say? What does the observer know about the random vector x, this unknown x? Well, all the observer can say is that this unknown x is distributed according to the measure mu. Okay, and if you want a confidence interval of 95%, well, you need to take some confidence set. You need to take some set with 95% of the mass of mu, and that's where x lies. Nothing better than that. This is the answer of the observer. However, if our Bayesian is loyal to his principles, then at a later time, they have some information. So the opinion about the distribution of x changes because of the observation. So they need to update the prior distribution, the prior opinion about the distribution of x, of this unknown x, given the observation. Okay, so we observed a specific sample of this theta s for s smaller than t. And how would you update it? Using the Bayes law. Bayes law tells you the following, that if you take a point x in Rn, you want to compute the density. You know what, let's imagine for 1 second that these are discrete random variables, that x is discrete random variables and theta t is a random walk, not a Brownian motion, because this way these are actually probabilities. In truth, these are densities, but let us suppose for a second these are probabilities, it is the same. Okay, so now once you observed something, you saw some information about theta t, now you need to update. What's my opinion about x? What's my current idea about the distribution of x? What's the conditional probability of x, conditional distribution of x, given this observation? And Bayes law tells you that, you know, the probability of A conditional on B is like probability of B conditional on A times these probabilities. It's a elementary formula. This probability is the so-called likelihood, the probability to observe theta t conditioned on x equals x times the prior, so times this and divided by the probability to observe theta s. Now these are not probabilities, but these are densities with respect to either Lebesgue or Wiener. Okay, but it's the same. I mean, it means you take a tiny region in your space. Okay, so this is the Wiener law. And now we can compute the posterior distribution. So we claim that the observer posterior distribution is what? Okay, so it is the probability distribution on x. Okay, this is the density of that x equals to x, given the theta that we observed. Okay, so for x in Rn, this should integrate the integral over x of this should be 1. And the claims that this equals to the following formula. It's theta tx minus tx squared over 2 times the original prior divided by some normalizing constant. Theta. Okay, this z is just a normalizing constant to make it a probability distribution in x. And what's this exponent here? Actually, if I just switch to another normalizing constant, let me write it in a better way, in another way. So if I switch another normalizing constant, this is what it is. You multiply, you take a Gaussian. Okay, so you take in Rn, if you observe theta t up to some time, then your posterior distribution is the following. You take theta t over t is the center of the Gaussian, or the center of a Gaussian, multiply by a Gaussian center at this theta t over t. Remember, that's kind of naive way to estimate x. You put a Gaussian of variance t, so this is root of t, okay, and you multiply by the original distribution of x that you had input earlier. So as t is larger and larger, your opinion is more and more concentrated because of this Gaussian factor. And when t goes to infinity, you really goes to a delta function at a point, which is what we expect. Okay, so this is the intuition because of the formula, but the proof is actually just this Cameron-Martin computation. Let's see. So what is the right what's the right hand side of this this expression here? What is it? So first of all, the a priori probability that x equals x is p0 of x, right? Normally in constant, I just call it z and not think about it at all. And now, what's the density of theta s given x? Okay, so what is this density? So this is the this expression. This is the density with respect to pt of what? Recall that theta t is ws. Okay, theta s, which is ws plus sx, right? To condition that the drift is x. Okay, so that's the right hand side of this expression. And we, by the Kammerer-Morton formula, we said that the density of this drifted Brownian motion with a fixed drift is this expression here. So this is how we know the posterior of the observer. Okay, now let me summarize what we did. So we have this family of distribution. By the way, just note the posterior. It depends only on theta t and not on the entire pass. Somehow it happens for the Liev-Impala version of the process that you only care about the last point. So the density given just theta t is the same as the density given all of, I mean, if you look on all time v40. Okay, so let me summarize what we know. So we have this family of distributions. Pt theta, family of densities, let's say, probability densities in Rn. Okay, so T is positive and theta in Rn. If theta t reaches the point theta, then this will be our opinion about the distribution of x. Okay. Now let's try to analyze this Bayesian strategy. Okay, this game. So let us denote pt. It will be p of t theta t. Okay, so this is a random density in Rn. Okay, so this is how would this observer, what would we analyze? What would this observer think? What would be the opinion of the observer about the distribution of x at a later time? That's what we do. And this is actually this stochastic equalization of Eldan. So what are the properties of Eldan's stochastic equalization of this pt? First of all, each of these pt, so with probability 1, pt is more log concave than e2 minus tx over 2. Okay, this is just because look at this formula. This is log concave, this is log linear even, and you have this factor here, so it's clearly more log concave than e2 minus tx over 2. And therefore, the isoperimetry constant at least root of t, always, I mean, with probability 1. Okay, very good. And the second property is that we claim that we have this decomposition of the original measure. Okay, so we claim that for any point x in Rn, this random density has expectation, which is exactly the original density. So we have a decomposition, this is the composition of P0 into a mixture of P theta's. This is what we obtain. In fact, this is a general property of Bayesian statistics. This follows from the complete probability formula, so if I so what's the expectation of PT of x? This is the expectation of PT theta t of x, right? Which is what? So the expectation is over theta t. That's the randomness theta t. So it's like the integral over put it the density of theta t. This would be the way I denote it, density of theta t, times the meaning of PT, the density of x equal is condition on theta t equals to theta, and this is just P of x equals x, or P0 of x just by the complete probability formula. Okay, and moreover, I know more than that. I know that let's write f sub t for the sigma algebra spanned by generated by theta t. So all events that can be described using theta t up to time, all knowledge of the observer up to time t. Then the same proof tells you that if you condition, so if t is larger than s, the expectation of PT's condition on fs will be ps of x. In other words, and this is the same proof, same computation. So in Bayesian statistics, it's always the case that the expectation of your future opinion, of your future probability distribution of the unknown, is your current distribution right now. This must always be the case by the complete probability formula. Okay, very good. Now, by the way, this Bayesian approach is the details are spelled out in my paper with Putterman. Okay, so now how would you use? So this is some construction. It has nothing to do with the isoperimetry so far. Now let me explain you the stochastic localization approach to isoperimetry. Okay, so this started with Eldan in 2013. So what's the idea? We constructed a certain family of distributions. I don't know, I analyzed in some way, but what does it have to do with KLS? So given some subset, we have this measure mu, given a subset E in Rn, whose measure is 1/2, P0 of E, which is the integral. This is a shorthand for the integral of P0 on E. This equals to 1/2, okay? And you remember by this Sternberg-Zumbrunn and Minor result, we need to show that that the boundary measure of E is larger than something. We lower bound for this thing. Okay. What is this thing? What is the boundary measure of E? It's the integral over E of P0. And this is the expectation of the integral of Pt on the boundary of E, right? Now, recall that Pt is more log-concave than a Gaussian. We know that the isoperimetric constant of Pt is not too small. And therefore, okay, this is the expectation, let me write, this is the expression of Pt plus of the boundary. So this is at least root of T times the minimum. Let me write the product, they are smaller than 1, so I can put the product of Pt of E times 1 minus Pt of E. Okay? And let's call this friend here M of T. So this is 1 minus M of T. Okay? And we have this lower bound, so this factor is okay if T would not be small. And the thing that we need to control is this process empty, the measure of the set E with respect to Pt. So let's say a few things about empty. So what do we know about this empty? So empty first of all, we know that it begins at 1/2, because P0 of E is 1. MT is just PT of E, and M0 of E is 1/2. And then it does whatever, some kind of process. And what we want, so we need MT in not too close to 0 or to 1. The number between 0 and 1. I don't want it to reach 0 and 1. I want it to be in, I don't know, 1/10, 9/10, for as long as possible. Why do I want that? If I can arrange MT to be in this interval for as long as possible, this implies if I can get it up to time capital T, this would give that psi of is at least a constant root of T, right? Because the boundary of E for any E is at least root of T. So and this is just a constant. So that's my goal, to make it not deviate too much from half, or not reach 0 and 1 for as long time for a long time. Now, there is one more important thing about MT, and this is the fact that, okay, so MT is the integral over E of PT, okay? And therefore, for T larger than S, the expectation of MT given the sigma level of S equals to MS, because this is just linearity of the integral. In other words, this is a martingale. Its expectation in future times is its current value. Okay, and this is a very good thing to know, because martingales are just time changes of the Brownian motion, basically. So what we know is that as time progresses, this process, what it can do it slowly or quickly, but it basically, you know, probability half jumps a bit, probability half goes down a bit. And the only question is, how much time do I wait between the jumps? Okay, what we need to show is it does not, you know, also the constant function is a martingale. I need to show that the so-called quadratic variation is not too large. Quadratic variation is not too large, and in fact, what happens to be the case? Okay, so it's not that hard. Okay, so it's not that hard to define the quadratic variation and to compute it here in this case, but I think that I will leave it for maybe tomorrow. I want to say something. So what you get? So it's not very difficult computation. What you get is that the expectation of MT1 minus MT, it is at least the value at 0, which is 1/4, minus the expectation of the integral from 0 to T. Let me put capital T, of the operator norm of a certain matrix, where AT is the covariance matrix of PT. Okay, at this step, so you want this to be, so we need this to be, I don't know, bounded. So we need this to be bounded by, I don't know, 1/8 or something. And then you know that the expression of MT times 1 minus 3 is at least some constant, and then you have a good bound for root of T. And this is what Chen did. So Chen was able to control the covariance matrix of PT. At time 0, A0 is identity because you are isotropic, and up to a certain time, so Chen, so up to T, which is was the things that he got, root of log n. Up to, okay, I lose a log n actually, but okay, up to something like this, maybe over log n. The operator norm is at most 3. So you know that you can get this T, and this is the way the argument proceeds, and it did that by analyzing third moments of the matrix and some bootstrapping and very interesting things. Okay, so I want to conclude by certain interpretations. So I'll skip some things. I go to conclude by interpretation to the Minkowski and Prekop-Lendler stability business, Prekop-Lendler. So what's the interpretation? Okay. So we have this random vector theta t, and maybe it's a bit better to look at theta t over t. So that's x plus a noise, Gaussian noise. The noise gets smaller and smaller as time passes. Okay. We know the distribution of this random vector theta t over t. So what is this? What is its distribution? So it has a density in Rn, which is our density P, convolved with a Gaussian, right? This is two independent things, so it's a convolution, and the Gaussian has variance 1 over t. Okay, this is the density. Let's give it a name. I'll call it rho of t for now. Okay, this is the density of theta t over t, but this is log concave and this is log concave. So by Prekop-Lendler, by Minkowski, this is log concave. Okay, if it's log concave, it means that its Hessian, the logarithmic Hessian, should be okay. You put the minus, would be positive definite. Okay, so this is positive definite, but actually it's not very hard to compute. And so this is actually t squared. There is, this is minus the covariance matrix at the point of I think PTTX. Anyway, this was the matrix AT at some point that we discussed earlier. Okay, so from what do we know from this property, for these bounds in the KLS? So from Chen's result, we get that if mu is isotropic and log concave, then if you take t, which is not okay, we want to reach a constant, but we reach something that okay, x, not that bad, over another log n. Okay, then so not only you know that the Hessian is not definite, but you even know that its minimum eigenvalue is not too small, because it's because AT is not too large, so the minimum is not too small. So the minimum eigenvalue of this convolution with respect to this measure rho t is at least, so what would you get? You'll get at least t minus 3t squared. That's a quantitative way to understand the log concavity of this convolution. And in Eldan's first paper, we used this method for finding stability estimates in Minkowski, but this direction, I think, was not continued. And my question too is it possible to find a stability version of Prekop-Lendler that implies good estimates towards KLS? Okay, and with this question, I'll finish. So thanks you for your attention.
Thank you very much. So let's thank Bo'az for a wonderful lecture. Any questions or comments? So please just unmute yourself if you want to ask a question. So let me maybe start with one question that I have. So I assume I'm trying to understand what would be sort of the spectral consequence of KLS. So one should be able, I assume, to get some universal lower bound on the Neumann eigenvalue, right? And which would be with some dimension independent constant.
Mm-hmm. The conjecture independent constant. Yes. What we know is a subpolynomial.
Right. So essentially, so if you have a convex, So what I'm trying to understand. So if we're thinking about just convex sets, so what you're fixing, you have to fix something, right? So you're fixing.
So isotopicity, the covariance. I put the covariance identity. That's the condition. Covariance of the measure is identity. Or small, if you want, you can make it in some direction. So in all, if you think about it as a random vector, the inertia matrix, the inertia ellipsoid is the Euclidean ball.
Right. Okay, and then so if you put it in this isotropic position, then you have a sort of a universal lower bound. That's the point.
Yes. For the Neumann eigenvalue, yes.
Yeah. Thank you.
For the Dirichlet action is also things, by the way.
Sorry?
For Dirichlet eigenvalues are also some things. I think there is a
really? What do you get for Dirichlet?
So first of all, it's larger. You get so the Euclidean ball. I think for the Euclidean ball dimension n, it's the Neumann is 1 over n times the Dirichlet, roughly. That's what I remember. I think. Am I wrong? No. I think.
Well, for Dirichlet, well, of course, I mean, you can just bound Dirichlet from below by the second Neumann. That would be correct.
No. So one second. So if you take a Biographie root of n, so the test function is just this thing. So it goes 1. Yeah, I think it's 1 over n. Yes. Yes, and there is up to log again something is known. So you can put a convex body in some position always, so that its volume and its first Dirichlet eigenvalue would be exactly like the ball up to universal constant. So this is also possible. There was a paper by Schmuckenschlager on this, and there is some
right.
That are not but there are also other things that are not written there.
Right.
I had some discussion with Emmanuel about that. Yeah, for this one, the argument you can also get something. But somehow all this idea of mixing and the applications in high dimension and I don't know, there are hundreds of papers about sampling for local distribution high dimension. So somehow for sampling and for mixing, the Neumann second eigenvalue that is influential. So that's one motivation for this study.
Right. Thanks. So other comments?
Can there be some discrete version of KLS, or I'm not
sure.
Yeah.
I think so. Yeah, on a lattice you can have log-concavity on a lattice makes sense. Just lattice in RN, I mean. Is that what you meant, or something much more fancy?
No. Some like as simple as possible.
So on ZN, you could have some things. You could have a function which is log-concave, and it's more complicated than in the continuous case, but there are some things. I don't.
Yeah, maybe not just on the lattice, but maybe on some other graphs. But yeah, maybe reasonably, homogeneous or something. Yeah. Anyway.
So I don't know. I remember that on a lattice, something depends very. So if you want to do, for example, the first thing we say, this Hensley little thing here. What was the Hensley thing? I said it also last time. What was the Hensley thing? That you can determine the from the covariance volumes of high-plane sections. And I remember that this does not work very nicely in the discrete world.
Okay.
Worse but maybe we just didn't find the right point of view. So there are some. It's a good question. What would be the right analog? I'll be happy to hear if you have any idea.
Okay. Thank you.
Thank you.
Yes, please. Yeah.
I'm just curious, what is exactly, if there is any advantage to the Bayesian perspective Oh, can you hear me?
Yes,
Yes,
yes.
it's echo,
Okay.
but
Sorry about this. Yeah. Okay, I'll try and say that again. Is there any advantage to the Bayesian perspective of stochastic localization?
So first of all, it is just for the construction and not so much for the analysis. It does help you understand some things. So for instance, okay, we discussed our estimate for X itself, right? And we understood it's going to be a martingale. But if we can also look on other things that will be automatically a martingale. So you can look on any function of X, and your opinion about it would be a martingale. So maybe that could be of some help in some analysis. I don't have say killer app for this Bayesian interpretation. One thing that it works nicely in Riemann manifolds. So you could do it. Okay, so it's not exactly the Bayesian interpretation, but the strong relation would be a heat flow. So you can have the composition of the total, say the Liouville measuring on a Riemann manifold into the through the heat kernel functions. Okay, so you could so there is such a thing that you could do it in other contexts more than this standard localization. This could be an advantage.
Okay, thank you.
Okay, so if there are no more questions, so let's thank Bo'az again for the wonderful series of lectures. And we will resume tomorrow with the first lecture by Yuan Sichen.